Thank you very much in advance, KATHRIN. We are really excited and always really happy with the collaboration with you.
Sure, Maru. Hello, everyone. Welcome back from the short break. Welcome, KATHRIN. So today we have Dr. KATHRIN SPENDIER, who is a quantum evangelist at Quantinuum. She holds a PhD in physics from the University of New Mexico and is also an associate professor with research affiliations at University of Colorado, Colorado Springs. She has also been a tenure-track faculty member and has worked on biophysical phenomena, condensed matter physics, and a lot more. She has been an active lecturer as well, taking numerous undergraduate and graduate physics courses. But today, she is here representing Quantinuum and will be hosting a software bootcamp for all of you. So yeah, and the stage is all yours, KATHRIN. Please take it away.
Okay, thank you very much for your nice introduction. Really appreciate being able to join the WOMANIUM Quantum program again this year. So this is always amazing. So can you show my, can you see my screen?
Yes, it's visible.
Okay, great. So yeah, thank you for having me. Thank you for the very kind introduction. I think it's an amazing program, and I'm super excited that we are participating again this year. From the Quantinuum side. So just to give you an idea, so today I'm going to talk about TKET, which is the Quantinuum software, quantum software development kit. And then tomorrow I'm going to give you a virtual reality lab tour of our trapped ion quantum computer. And then you will have a panel discussion with one of our scientists, Carolyn Figgett. And then we're also going to be part of the career fair, like a few career talks today, this week, I think on Friday. So so we have a lot of Quantinuum this week, which is a good thing, I guess. So today I'm going to talk about improving quantum circuits performance with TKET on the H series devices and also other platforms. So the idea here right now is to speak, for example, about like 30 minutes to give you an idea about TKET and Quantinuum in the H series, the features the H series has, and then we'll go into a coding exercise. So for those who don't know Quantinuum yet too much, I just want to outline that we are a global company. We have our headquarters are in Broomfield, Colorado. I'm actually right now in Washington, DC. I'm calling from Washington right now, from our Washington office. But we also have a UK and office. We have Oxford, London, and Cambridge. This is where our software team sits. So before we were Cambridge Quantum on the software side, and then Honeywell Quantum Solutions on the US side, they merged to form Quantinuum. And then after the merger, we opened offices in Tokyo and Munich. And then here on this side, I just want to say that we have people that are clustered in specific domains. So trapped ions, we are running in the US, and most of our quantum algorithm and software development is in the UK side. So I want to talk about our software stack briefly. So what we're going to focus on today is TKET, which is our open source quantum software development platform. TKET, you can think about the middleware or kind of the glue if you are interested in applying a classical problem, rewriting it into a quantum language, and then solving it on a quantum computer. So you have cybersecurity, quantum chemistry, we focus on AI and machine learning. So we develop tools, right, with algorithms that then are rewritten in a quantum circuit, for example, that is fed to TKET. And TKET then is our compiler that either helps you run the circuit on like IBM or IonQ or Rigetti, and then also our H series devices. So this is our full approach regarding TKET. And I want to say that TKET kind of, initially before there was the merger between Honeywell Quantum Solutions and Cambridge Quantum, TKET was really developed to be like agnostic, to have lots of different front-end applications and back-end applications. And this is kind of like why TKET is very functional. So the agenda for this TKET workshop is to give an introduction to TKET and Quantinuum H series, then go over some PyTKET coding examples. And then I'm also going to talk a little bit about PyTKET Qiskit, which is our Qiskit extension. And then please also do let me know if you have a question or something, because I can't see the chat or something right now. So this is again kind of like outlining what is a full stack quantum computer for gate level based quantum computing. So you have a problem definition, right? You want to solve. What you do then is you implement your algorithm, and then the algorithm, whatever favorite language you use, could be Python, right? Could be C++, could be Rust, could be I don't know. Actually, MATLAB now. I think MATLAB has a quantum toolkits or tools, and then also Mathematica. You know, could whatever kind of language you want to use. Whatever you do use, you have to get a quantum circuit, right? A quantum circuit, as you know, these are the instructions we want to send to a quantum computer. But these instructions are a quantum circuit, right? These are these gates. You prepare the states and such. But that's a very general way of representing your circuit. It could be written in Quasm, right? That's a language we use in order to share our circuits. And then it has to be sent to a quantum processor, which could be, you know, the hardware or quantum simulator. So in between, you have this quantum compiler, and TKET is a compiler. Other compilers, you know, are Qiskit, for example, Cirq, Q#, PennyLane. They all have their compilers as well. So in essence, if you have to develop something here, you have to run it here. And for this, you need a compiler. When you do this, you have to keep something in mind. You have to keep in mind that you have a lot of different backends nowadays. You have superconducting quantum computers, trapped ion, photonics, and other technologies. And all of them have a different language. So their backends have a different language, and you have to keep that into mind. So if you want to test your quantum algorithm on different you know, backends, you want to have that kind of like smooth. But then because you want to have this smooth, you have to consider different things. So here I just want to outline different architectures. So you have the H2 series of Quantinuum. This is our racetrack where you have 32 ions go around a circle. And these are fully connected, so each ion can talk to each other ion. And then you also have basis gates, right? So for example, if you have a Hadamard gate, you have to rewrite that gate into these basis gates the quantum computer can actually implement. So if you want to run my circuit onto the H series device, I have to keep this all in mind, all-to-all connectivity and the basis gates. So now I get my result, and now say I want to run it on the Eagle device and the IBM. So now I have a different architecture I have to take into consideration, a different set of basis gates. So here at IBM devices, you don't have all-to-all connectivity because the qubits are on a chip. So you have to map your circuit onto this chip, for example. And then Rigetti, on the other hand, has even a different approach, different basis gate sets again, and their architecture is again different from IBM. So if you talk about a quantum compiler, just like TKET, for example, it has to consider all of this, the connectivity, basis gate sets. And then if you look closely here at the IBM device, you can see different shades of purple. That means that each of these qubits have a different error. So now you also want to map your circuit. For example, you can have, if you have, you know, 1, 2, 3, 4 qubits or 5 qubits, you want to maybe put the circuit onto here instead of onto here where it's dark purple, because you want to minimize the noise. So your compiler also has to do noise aware mapping. So this goes back to just a tool for you to estimate how good is your computation you're going to be running on your quantum computer. What you should be looking at is the 2-qubit gate fidelity. So that means like how well can you implement a 2-qubit gate on your quantum computer? If you would have one would be your perfect 2-qubit gate fidelity. So that means it's a perfect, you don't have any kind of noise. So when we talk about fault-tolerant quantum computing, we would like to have a gate set of qubit fidelity that is 1 for single qubit gates, for 2-qubit gates, for measurement gates, and such. So this would be fault-tolerant quantum computing, but right now we're in a NISQ era, so we have noisy operations. So here I just want to show you what's the difference between different fidelities. So what I'm plotting here on the x-axis is the number of 2-qubit gates you would like to implement, which is big N. And on the y-axis, you have the total 2-qubit error, which is calculated here. So 1 is your perfect fidelity, minus the fidelity of the operation you have to the power of n, so the number of 2-qubit gates, and then times 100. So to give you an example, so if you have 102 qubit gates with a fidelity of 0.993, after 102 qubit gates, you already have 50% error. If you have 102 qubit gates with a fidelity of 0.999, suddenly you only have 9.85% error. So I want to pay attention here. By having like 0.993 to 0.999, you were able to run way more 2-qubit gates than before, right? And the error is just really much lower. So here I show you 25% line. So you can say, well, if my 2-qubit gates fidelity is 0.991, I can implement 31 gates before I have 25% error. Or if I have a very good device, 0.998, I can implement 142 qubit gates before I collect this error. So I want to put this out for you to be knowledgeable about what you're actually running on a quantum computer. So if your quantum computer has a 2-gate fidelity, people should share that with you. That should be in your hardware knowledge. It kind of gives you an idea like how deep of a circuit, how many 2-qubit gates can I actually run? Is the result I'm getting from the quantum computer meaningful? On top of that now, I want to show here is that the crux of NISQ devices right now is to reduce this number of 2-qubit gates. So can you do some smart things in order to reduce the number of 2-qubit gates so you can decrease this noise? And this is what it is all about. So just to give you an idea, superconducting qubits typically sit here between 0.991, 0.995, and trapped ion qubits sit more on this side, 0.996 to 0.998. So this is why you hear often about 0.999 regarding 2-qubit gates, because that's kind of where we want to go as an industry. And then if we have these kind of noisy qubits, and then we add logical qubits on top of these physical qubits, then it looks very promising for us. But we still need to get this curve lower. So we're still working on getting this curve lower, and Quantinuum is working on that very hard. So when you are a quantum information scientist who is interested in applications, and you want to run your gate level quantum computer to solve your problems, you want to program in your favorite language, you want to run your algorithm efficiently, you want to get the most out of your algorithm, right? So you want to reduce this number of 2-qubit gates. That's all it is. Reduce this number of 2-qubit gates, put it on your device in a smart way, make use of the basis gates, right? Can they help my algorithm and such? So this is what you want to do, and a compiler should help you do that, right? A compiler should take some of the pain away for you to worry about all these things. And this was TKET developed. So I think a lot of you don't know that TKET actually was started to be developed in 2014. So it's almost 10 years into development, and TKET was developed in this in mind, because you have so many different backends, they do different things. You would like to take your favorite language you like to code in, Python, Pennylen, Circ, or such, and then you can run it through a TKET compiler and then run it on the backends you would like to run it on. So this was TKET developed for. It typically fully focuses on making your circuits more efficient. This is what TKET was developed for. This is what the TKET team is working for. So TKET is used to rewrite the circuits. It's a C++ library, so you can speed up the compilation process, because you can imagine the bigger your circuits are, the harder it is to optimize them. Because many of us don't know how to code in C++, there's a Python wrapper. So around TKET, which we call PyTKET. So this is what you install. When you do pip install PyTKET, this is what you install. And now once you have a Python wrapper, you can talk to your favorite languages. This is like, for example, IBM Qiskit. You can take the Qiskit circuit, call it into TKET circuit. Then you can call the compiler to make your circuit most efficient based on the information you have for the given backend. So it could be Quantinuum, IBM, IonQ, AQT, AWS, AQM, and such. So you can do this. I know, for example, QBraid, they have TKET transpiler. So if you like to work with QBraid, you can actually also take advantage of the TKET compiler if you wish. Or you can just code yourself in a Python library, right, in your own environment, whatever is your choice. So here, I think this is something people don't know about TKET. TKET is immense. So we have a lot of different extensions. So besides pip install by TKET, you can also do pip install PyTKET Quantinuum. Then you can talk to the Quantinuum devices, pip install PyTKET Qiskit, that would give you the IBM access, IonQ, AQT. So this is how you have the different devices and simulators. Then we have pure simulators, for example, QJAX, Quarks, and then transpilers. So when you want to go, for example, you want to use the PennyLane library, you can do that too. And then you can go from PennyLane to TKET and then TKET to PennyLane. So there's overall many of these, I think 16 to 18 extensions we have, which is very extensive. Okay, so now let's talk about the compilation tasks, because that's what we're going to be focusing on today a little bit when we code. So I told you we have to solve for the constraints for the backend, the architecture, and the gates it has. And then we have to optimize the circuits. We want to preserve the semantics of the circuit, right? So that it does what we're supposed to be doing, but we want to make it smaller. So we're going to have less operations, specifically less 2-qubit operations, because they are the noisiest in gate-level quantum computers. So this is just some things about TKET. So if you have IBM Q Quiddo, which is 1, 2, 3, 4 qubits, these are the basis gates, right? So TKET has passes that can help you. We call auto rebase pass, which you can define. We'll play with this a little bit. So you can take your circuit and you can rewrite it into the basis set of your device. Also, what you can do, you can have displacement, which we call noise aware placement. If you can place the circuit onto this architecture. Okay, so we can consider the colors here, different noise levels, and we can figure out if we want to place, how we want to place the circuit on here. Because we, for example, at the IBM device, you don't have full connectivity. So in order for 1 to talk to 4, you have to implement swap gates. But each swap gates is a 3-qubit gate, 2-qubit gates. So this is very expensive. So if you can put your circuit on here in a smart way that you reduce the number of 2-qubit gates, you will gain by having less noise when you run it. So TKET does that for you. TKET also looks at optimizations. For example, if you know, we talk about unitary matrices, so our operators are unitary, right? When we have an H gate or X gate or such. So if you have 2 unitary operators after each other, right? It's just like having an identity matrix. Or here, if you have these 2 qubit gates and a phase gate, it's better to rewrite it into 1 2-qubit gates and a couple more single qubit gates, because single qubit gates are less noisy than 2 qubit gates. So on a noise budget, rewriting this as this will help you. So there's a lot of different rewrite rules. So TKET looks for these rules, looks for these passes. We call it peephole optimize. And then it looks for these things and tries to optimize your circuit by making it more compact, making it smaller. We play with this too in the code. It's called from PyTKET.passes import remove redundancies. So it looks for these features. For example, if you do 2 rotation gates after each other, it's better to just do 1 rotation gate, right? Because we just do, instead of doing Rx once and then again, we just add these angles together. The same thing here, I told you, these are 2 the same gates you apply, so you can just get rid of them because they would be the identity matrix. And here again, 2 are Y rotations, we just combine them. And this is a nice one, which I think sometimes we don't appreciate, is that we are measuring out on the C-axis, right? So the C basis. So a rotation around the C-axis at the end makes no sense because I'm just rotating my vector in a block sphere around. So I can get rid of this as well. So what you have, if you have a circuit, a TKET circuit, a PyTKET circuit, you can just do remove redundancies. You can apply the pass to it. We'll play with this. And you can see that you significantly reduce the number of gates, right? so it's very powerful. So we combined these, we got rid of that. This is a phase, no angle, so we got rid of this. There's no RC rotation because we measuring out on a C basis, so we don't need that. So TKET takes all this into consideration. And I want to say that TKET has many compiler passes. It is an exhaustive list. For example, we also have ZX calculus implemented in TKET. So it looks for features in a circuit that can be rewritten in a ZX calculus term more efficiently and brings it out of ZX calculus space back into the gate level space we're used to. It also looks at phase polynomial, phase gadgets, architecture, where we already talked about mapping. It synthesizes from many qubit operators, right? So we have a Toffoli gate. You can't implement Toffoli gates. So you have to rewrite that into 2 qubit gates. So TKET does this all for you. And TKET is developing and increasing in the features. So as you can see here, in 2018, this is kind of like when we got it in GitHub, but it's just looking at GitHub features. You can see that we have been increasing our number of features over and over. So this is just for PyTicket. PyTicket Quantinuum has their own plot like this. PyTicket Qiskit also has their own features. But I just want to note something here. If you just look at the number of features PyTicket has been adding over the years. So this is when we became open source for the community to contribute. And I just want to see, like, you see how many more stars you have here compared to here. That just means that really quantum computing is accelerating. More and more things are happening. So we, more and more features are added because we are very active now as a community. And this is really exciting to see, right? It doesn't slow down, it's speeding up. So this is pretty cool. So I told you we have all these different features, right? I told you we have all these different passes. In order to help you to get started, TKET has this get compiled circuit pass, which we will play with too today. So you implement your circuit, and then you have different optimizations level you can play with, up to 0, 1, and 2. 0 is just rewriting into a Casey-Spade set, and then putting another architecture. Level 1 has some minor optimizations, and level 2 has the biggest optimizations, so the most optimizations, right? Has a lot of passes applied to it, but you can also make your own passes because maybe your circuit is very special and there's a special pass that is not part of the default pass that you want to add. So TKET has this feature as well. Then we're going to play with this too a little bit. You can target different devices easily. So for example, in PyTicket, if you run on a Quantinuum device, and then you want to run on the IBM device, you add a few lines of code, right? Initialize your IBM device, and then you can just compile your circuit using TKET and also run it using TKET if you wish. Okay, so this is just an example. We'll do that too. We'll do some coding examples here, but this is a H2 circuit for quantum chemistry. You can use the circuit to estimate the ground state level of your H2. And I just want to show here, this is the circuit. These here, you see these ladders, these are called phase gadgets. And they can actually be very efficiently rewritten in ZX calculus. And TKET uses this. So to show you, if you want to run this circuit on the IBM backend, for example, and you just don't optimize, you just route and place it, you have 56 2-qubit gates, and the correct answer is 1010. And out of 100 times, you get 35 times the right answer. If you run it through TKET with optimization level 2, you can reduce this here because of these phase gadgets, which you can rewrite in ZX calculus, to suddenly 19 2-qubit gates, right? So now you have more than 60% of the time the correct answer. So reducing the number of 2-qubit gates is very important because it improves the quality of a result. Now, to give you an idea what happens if you run it on a trapped ion device, in this case, the H1 device, we use the emulator here. But in any case, you take the same circuit, right, this here, and you rewrite it. TKET rewrites it with optimization level 2, which is one line of code, and then you have 18 2-qubit gates. Because it's fully connected, you have you know, a few less gates, but then on top of that, the correct answer is almost, you know, 92 times out of 100. And that's because our gate fidelity compared to superconducting devices is better for trapped ions. So this is where really like the powerfulness of trapped ions comes out. If you are interested in making your qubit most efficient, your circuit most efficient, trapped ions are very good devices to run it on. If you right now worry about speed more so than qubit efficiency, then you know, superconducting is the choice you want to go with. Superconducting devices also have, you know, error mitigation techniques that you can use. So in any case, it's you know, depending on what you want to do, but it doesn't matter what you want to do. You always want to reduce the number of 2-qubit gates. So right now in NISQ era, that's important. And also, like, obviously you want to reduce how deep you go with your quantum circuit, right? Because of coherence times as well. So now I want to talk about the H series and the unique features of it and how TKET comes into play. So we're using quantum charge coupled device architecture, which is fully connected. So this is what I mentioned already. So we are fully connected in a trapped ion computer. So you can, if this qubit wants to talk to this qubit, we at Quantinuum, we physically move this trapped ion to this trapped ion, and they interact, and we can then do the gate. In another chip, like superconducting chip, for example, you may have your qubits lined up like this. So they have to go through the chip, and you have to add these swap gates. So every time you have to add a swap gate, you have to swap this to here, swap this to here, swap this to here. You have to add 3 2-qubit gates. So this is very noisy if you have add this compared to one of these. Then also we have arbitrary angle 2-qubit gates, single 2-qubit gates. So that means that we can do an arbitrary angle. So if you have to, for example, quantum Fourier transforms, typically you have to do very small angles. So the smaller angles you can do, the less error you have. So we have arbitrary angle capabilities with our trapped ion quantum computer, which is very unique. Then also you can do mid-circuit measurement and qubit reuse. So if you have a qubit which you want to reuse, measure out the value, maybe for error correction code or something, you can reinitialize that qubit and go ahead. The difference here, you have seen mid-circuit measurement also for trapped ion quantum computers. The difference here is that we actually do a trapped ion, you do a real reinitialize. So you take the ion and you apply the initial initialization routine you normally do when you load your ions. In a superconducting chip, you actually apply an X gate here. So if after you measure out the qubit is in 0, you do nothing. But if the qubit is in the 1 state, then you apply X gate, so it's in the 0 state. So mid-circuit measurement is a little bit differently implemented on a trapped ion quantum computer compared to a superconducting computer. And then you also have conditional logic, right? Do something, perform a gate. If your classical register reads 1, else do nothing. So this is very important for hybrid computation when you like send it to a classical computer and you have a classical routine, but also obviously for error correction. And then we have very good gate fidelities. So this is what I want to say here right now. If you look at the 1-qubit gates for a trapped ion quantum computer, it's 99.9996, right? So 100% would be perfect. And then 99.8, that is for your 2-qubit gate fidelity. So you can see this is like 2 orders of magnitudes different. So really, for trapped ion quantum computers, the 2-qubit gate fidelity is still the pain point, right? We also have state preparation that's similar than as 2-qubit gate. And measurement crosstalk is very low. So that's also something to consider. So in TKET, when you do TKET, you can do this arbitrary 2-angle qubit. So what I want to show you here is that obviously you can rewrite the CC gate, or the RCC, which is your arbitrary angle 2-qubit gate. So the fully entangled 2-qubit gate, right? This is the pi over 2 rotation, but here you have any kind of angle. And I want to say here is that this is where it becomes interesting. So if you have a C naught, a RC, and a C naught, you can rewrite that in the Quantinuum device as a RCC gate. So you can see that obviously two 2-qubit gates are way more noisy than 2-qubit gates. So again, with our unique capabilities of doing this with our device, we can reduce this number of 2-qubit gates, which then allows you to do deeper circuits and accumulate less error. So mid-circuit measurement and qubit reuse, going back to what I had said, is also a feature of ours. It's important for quantum teleportation, quantum error correction, which I said. So there's a code which we have in the example notebook I want to show you. And then also you have feed forward for quantum state preparation. So this is something we will be talking about too, if you would like to. So qubit reuse, why is it so powerful? As you know, trapped ions are really, really good with qubit fidelity, but they don't have that number of qubits, right? We don't have that many qubits like a superconducting qubits machine like IBM has. So qubit reuse allows us, for certain algorithms, not all of them, allow us to reuse the qubits. So if a qubit is done and you can measure it out, we can then reuse it for something that hasn't started. That's kind of the idea. So you measure the qubit out, and then you reuse it for a later point. If you do this, for example, for our 2-qubit, 20-qubit machine, which is our H1 series, and then we have the 32-qubit, which is our H2 series. But just to make you aware of this, so you have an 80-qubit circuit, that a QAA circuit, which is 80 qubits, wide, right? You can use qubit reuse and mid-circuit measurement to make it fit on a 20-qubit machine. For the 32 qubits, we can actually have shown recently with our launch of the H2 system that you can take a 130 qubit QAA qubit circuit and put it on 32 qubits with this mid-circuit measurement. So I want to say that this is only working on the trapped ion devices at the moment very well, because when you have superconducting devices, the mid-circuit measurement works well if you can map it onto like qubits that can talk to each other. If you have many qubits, again, in your device, the swap gate will overtake the noise again. And whatever you win from mid-circuit measurement, you lose because you have to add these swap gates. But this is very powerful. And if you are using the H series, you can actually utilize passes that help you to do this mid-circuit measurement. So let's go into the Quantinuum system workflow. When you get access to the Quantinuum system, I can show you how you can get access in just a little bit. We have different tools that help you run on it. So first of all, we have something called the syntax checker. Then we have the emulator, and then we have the hardware. So the syntax checker is there for users to ensure that your circuit can be run on the hardware before submitting it. So for example, you will make sure that it uses the right basis gate set, right? And so it checks for the syntax, and you can use this for free, and that's called HQCs. So HQCs is our H system quantum credits. So you have heard about credits. So Quantinuum also has credits, and we call it H system quantum credits, HQCs. Then there's something called an emulator. So please take note, we don't call it simulator, we call it emulator. And we call it emulator because our emulator tries to model the whole workflow when you send it something to a hardware. So it models your compilation, it models like how it goes through the software stack, and actually is going to be implemented on the machine. And then it also models the realistic physical noise models of the device. So it models when you shuttle ions around. It models when the ion just sits there and waits. It models when you apply to qubit gate, what is the error, and such. So the emulator, when you run that requires HQCs. And it is a very good testing tool. to make sure that your circuit is perfectly aligned and your work works well before you run it then on the hardware, which also requires HQCs. So when you get access to a Quantinuum device, this is what you're going to work with, which is called HQCs. So how do you estimate HQCs for our system? So here, this is the formula. So you have 5 plus the number of 1 qubit gates plus 10 times the number of 2 qubit gates. That's 5 times n sub m. So this is the SPAM operators, measurements. So state preparation and measurement operations divided by 5,000, and C is the number of shot counts. So if you look at here, the Bell state, for example, you have 2 single qubit gates. So that would be, I actually did this, realize. I did this calculation wrong. Yeah. So there should be a 2 here, and then 10 plus 10 times 2 and 5 times 4, right? So you have 4 here because you have 2 times you have to prepare your state, and twice you have to measure it out to get your shot count. So I will correct this because this should be a 2. And then this is your shot number, and that's 5 divided by 5,000. That gives you the HQCs. Then when you run it, when you access the Quantinuum device with TKET or KISSKET or whatever, you have different options. You have the H21 machine, which we call the H21/1. These are 32 qubits. We have H1/1 and H1/2. These are 20 qubits. You have the emulator. If you run it on the emulator, it's going to get a little E attached to here after this device name. And when you have a syntax checker, it's going to attach the SC in the back. So now let's talk about PyTicket Quantinuum. So PyTicket Quantinuum, which when you install that with pip install PyTicket Quantinuum, it provides you access to the H series, given that you have an account with us, or through Microsoft, for example, Azure, you can set up a free account for that. It can offer you the default passes. So TKET is automatically applied to your circuit when you submit it. So you have to turn the optimization off if you don't want to use TKET. It uses the mid-circuit measurement and reset option. It calculates the cost of your calculation, so how many HQCs you are using. And then you can also retrieve partially your result. So when you run the circuit with TKET, or PyTicket in this case, PyTicket Quantinuum, you can get your results out of the circuit before you even get your final result. So it gives you a partial result, which can help you troubleshoot if you want. You can also do batch submissions. So remember, there's something called session in IBM Q, in KISSKET, you can submit sessions and batches. So you can do something similar on the H series devices with patching circuits together. And then, which is on development right now, you can either submit QASM or QIR code, which is, allows you language control when you do circuit submission. Okay, so this is maybe something you should keep in mind. You want to maybe take a picture of this if you want. But this is how you get access to the H series computer right now. So Oak Ridge National Laboratory has a quantum user program you can sign up for. So you have to work with university, for example, where you have a project. Then your PI can submit an application for this. Then you have Microsoft Azure. There you actually can submit, you can log on, you can get $500, I think, free access. But the nice thing about this, if you have an Azure account, you can use the syntax checker, for example. That is free for you to use. Using the Azure account, you don't need HQCs. And then the other access, you can do it through in Quanto. So if you're a quantum chemist and you want to work with quantum chemistry algorithms, in Quanto gives you also access to our H series. So this is how you get access, and that was kind of like an overview of the kind of like the features of the H series. And now we want to go into a coding example. So before I do that, can I ask if there are any questions? Because I want to make sure that you kind of understand what TKET is for, what it was developed for, but then also understand kind of the features of the H series. I just want to show before we go into coding that you understand the kind of like the background.
Yes, Catherine, absolutely. I would start filling the questions. Do you want to rather just give a brief introduction of the coding session and tell them the installation instructions so that those who do not have the questions can start with the installation process?
Oh, sure. We do it again because we already did that before. So where's my stop share button now? Huh. Can't find my stop share button. Oh, here it was hiding. Okay, so so how many of you have QBraid set up? Most of you?
Yes, I think most of them have QBraid set up.
Okay, so so I guess we can just go because I did post that in the Slack channel. Oh, sorry, what is it called? You don't use Slack, Discord. So all you need to do if you go into the software bootcamp part. See if I have that here. Yeah, I guess it's just get started with the coding. That might be easiest. So that's okay. Okay, so just start with the coding. So what I would do is just if you're in QBraid, I don't have QBraid open, but all you need to do is you open up a new Python notebook, and then all you need to do is right now to install PyTicket and then PyTicket Quantinuum, if this is ever opening. Okay, so you just do pip install PyTicket. Okay, and then you run that, and then you also do pip install PyTicket Quantinuum. So these are the two things you need to set up. So if you have QBraid running, these are the two things you need to set up. Okay. So I can, while people set this up, I can field some questions.
Perfect. Yeah, thank you. So yeah, there are a lot of questions in this call, and I will ask one by one. The first question is regarding the optimizer and the transpiler offered by TKET. So how is that transpiler and the optimizer different from that offered in-house in the backend of IBM?
Oh, so it turns out that TKET was always a third-party provider to IBM. IBM actually has extensions for PyTicket. The thing is that we have really, so TKET was really focused on making it more effective, more efficient, the circuit compilation. This is what the TKET team has been doing. That was their focus on. So it turns out that we just have a little bit more passes. We have implemented and ZX calculus on top. That just makes it a little bit, for certain circuits, TKET works very well and better than Qiskit on average, the average transpiler. I will show you an example with a random circuit to just show you that for a random circuit, you can get better output with TKET. What I want to tell you is that there's no such thing as the compiler. What I want to tell you is that if you get to the point where you want to get the best out of your quantum circuit, when you really do research, anything you can squeeze out helps. So if you need to compile in Qiskit and then in TKET, and then you need another compiler, if you want to match compilers, do that. The best thing is to compile multiple times in order to get the best out of results. So there's no recipe that is like bulletproof, but I just want to tell you, you should try.
Thank you. Another question is regarding the optimization of the circuits itself. The question is, what are the different metrics that you consider while optimizing the circuit? Is it just the circuit depth? Is it just the number of gates used? What is the exact number of metrics you use?
Well, obviously it depends on your device, right? Because you have the connectivity too. Then obviously it depends on your algorithm, right? If you have an algorithm, if you do error mitigation, for example, right? You're adding circuits after circuits. You want to blow up your circuit you add noise, so you can figure out the noise model and then kind of figure out what would be the exact value for a given, like energy value or whatever you want to look at. But so it depends on what you want to do. So you have to be careful when you optimize the circuit, what you want to optimize for depending on your algorithm. If you want to run a Fourier transform, quantum Fourier transform, you want to make it small. If you run a Shor's algorithm, you want to make it small, right? If you run a quantum error correction code, you want to make sure that you put barriers in there so that your compiler doesn't squeeze stuff together. You don't want it to be compiling. So it really depends on your application.
Excellent. Another question, now this question is more on the hardware end. And the question is that you mentioned that you can physically move around the qubits to ensure all-to-all connectivity on the H2 system. Now, could you please elaborate a bit more on that? Like, how do you physically move the qubits? And a follow-up question on that is, how fast is it actually possible to move around the qubits on the system? Okay, so
we move. So I will have the virtual reality lab tour tomorrow, and I will show you a video there. But pretty much you use RF field, radio frequency fields, to trap your ion, which is charged. And each of these ions have their own trap, which is on a chip. And then with DC voltages, you move them on a chip. So each of them have a trap, and you move them on a chip. So that's what you do. Like, you move them around. You have them trapped with the DC field, and the radio frequency field traps them. And then when you move them across the chip, it's like the movement, the swap gate, for example, is like 40 milliseconds, to give you an idea. Was it microseconds? No, sorry, 40 microseconds is when you move them around, no milliseconds, microseconds. Yeah.
Right. One last question before you could start with the demo. This question is regarding the emulators you mentioned. And the question is, how many qubits can be simulated on the emulator using a single GPU? And if that does have a multi-GPU option as well? Okay, so that's a good question. So really depends on, as I said, it depends on the hardware you're using. Our emulators right now, we have some of the CPU and a GPU mixture. The emulation process is more expensive because we are emulating all the error in the model, the way you move the ions around. We model the stuff going through the full stack, right? What happens when it gets actually rewritten for the hardware language. Obviously, that needs more computational resources than just doing simulated like a real qubit, right? So I think we around 20 to 30 qubits or something, the emulation process is going to be slower than the actually running on the hardware for our device. But as you know, if you use like Frontier or one of the big clusters, you can probably go to like 50, 60 qubits, right? If you don't have to emulate the whole process. So we have the emulation on top of it. And I really don't know about the nodes. I think I'm not a high performance computing person to know about this, but I can tell you that the emulation takes more resources than just simulating qubits. So 20 to 30, the emulation process is going to be outperformed by a quantum computer, actually. Yeah, sure. Thanks a lot for that. And while I note down the rest of the questions for your later discussion, I would request you to please start in the software bootcamp.
Okay, cool. So so now you're knowing about and I'm going to, so what is the time? Like 11, like in 45 minutes, right? Is that correct? Okay,
yes.
Good. Okay, so so now I want you to look at the following. So you go to your you download your PyTicket Quantinuum main. So this is I just test. This is on something I added, and then you should have this example notebook here. So you click on examples, and then you have a couple of different folders. So what we're gonna go over right now is compile, Quantinuum compile without API, so you don't need a login. And then I would probably gonna go over TKET using with KISS-KIT too. This is a folder I'm gonna share with you because later on, and then also quantum mid-circuit measurement is something we go through. But in order, for example, do your homework, arbitrary CC notebook is something you want to look at. For example, emulator is a little bit about the noise model of the emulator. So if you look at this file, it tells you really about the process of emulation. So how much noise actually goes, noise considerations go into a system like this, and how you can turn these things on and off. So let's click on compile without API. I think I already had that open. Yeah, here. Okay. So so first of all, in PyTicket, you have when you are developing defining a circuit, we have the circuit class, and then op type, that's for your gates. And then from PyTicket circuit display render circuit, this is our rendering tool. So here you are making a bell state, apply the H gate to 0, to qubit gate, right? And then you measure all. So you can run these two, and then you do circuit rendering, and you can see that you get the circuit out. One feature that TKET has compared to KISS-KIT is that you can actually, after you define your circuit, you could just put everything in one line, which is nice. So you don't have to rewrite it, and you can run it this way. So that's nice. So you don't have to worry about rewriting in different light. You can just append it sequentially. And then also, I think our circuit rendering tool is super cool because this is your normal output. But look at this, you can render to ZX style. So if you're doing ZX calculus and you're interested in ZX calculus, this is the ZX calculus representation. You can also download your circuit. You can save it for your paper, so you don't have to do a screenshot if you don't want to, which is also pretty cool, I think. So that circuit rendering tool is pretty cool in PyTicket. So now we want to set up a backend. So for you here, so that you can actually work with compilation and play with this a little bit, we'll use the machine debug mode. So you are importing PyTicket extensions Quantinuum. We import the Quantinuum backend. In this case, we do the machine H11E. So this is emulates our 20 qubit machine H1-1, and E stands for emulator, right? Once we define the machine, we define the backend. So you have the device name, you put the machine in here, right? And then machine debug true. So this is how you access our backends without the API. Then we can look at the gate sets of the API. So so we just run this, right? So let's see, hopefully it likes me. Yeah. So now when we can do import extensions backends, you can look at the gates we have, and this is all the gate sets. So there's a lot of stuff here. So uptype, phased X, RC, CC max, and then some other barriers. You can import WASM, for example, and then some other stuff you don't have to worry about. But these are the gate sets, the gates you're using. So you can see something here. We actually don't have a CC phase. So you can actually add your CC phase gate to your gate set by running this. And now, oops. Maybe we have to run this first. So now you have all the gates the Quantinuum device uses. Okay, so let's go into circuit compilation. So I told you before that we want to remove redundancies. We want to make the circuit smaller. We will maybe use ZX calculus and such. So this is one command, which is called get compiled circuit optimization level 2, or 1 or 0. So here again, level 0 is just solves for the device constraints. Level 1 for optimizations. Level 2 has the most extreme optimizations. And this is the default level in PyTicket. So you actually can go to these links here. So if you go here, and I share this file with you later because I added these links in here. But if you go to the Quantinuum website here for PyTicket Quantinuum, we can see all of the optimization passes that are applied for you automatically. And you can look at all of these and they tell you what they do. So let's try this. So we have now our circuit optimization level 0. So if you run this, you can see it rewrites it just in the basis gate set. And we can look at the number of gates. So in this case, we have 22 single qubit gate and 1 2-qubit gate because it's a Bell state, so that's not very exciting. But just to show you here, remember how do this? Yeah. Remember how we talked about what TKET does? So it looks at all of these gates, right? So this is all of phased X gates. We can combine this, for example, into one gate. So when we do optimization level 2 here, we expect that we are getting a better optimization. So we run this. And sure enough, the circuit is way more compact now, right? So it works better this way. And then if you just look at the number of gates, so this is the call here, compiled circuit number of gates. If you do that, you can see a total number of 6 gates and a total number of 2-qubit gates. So this is when you want to call out how many gates you have, because this is a code I added here. So you just do your compiled circuit, which we called here, right? Dot n_score gate. That gives you the number of gates. Oh, this didn't like me. Why? Oh, gates, sorry. So 6, right? So this is the command for 2-qubit gates. Okay, so this shows you now how to do the compilation. So now this is something which I added to the notebook to show you how this works. So now imagine you want to take the Bell state circuit, right, which we have here, and we want to rebase it into the IBM gate set. So you do that simply by you type in from pyticket.passes import auto rebase. So auto rebase is a pass you can do yourself in TKET to rewrite now. You define the auto rebase pass as optite.x, sx, rc, and cx. So these are the basic gates for your IBM computer. So then once you have the rebase gate set defined, you can apply it to your circuit, and then you can do circuit rendering. So when you do that, as you can see here, now we've rewritten the circuit in the IBM basis. So I want to tell you here that this is pretty much what TKET does automatically for you. So it rewrites, if you, for example, install PyTicket Qiskit, it does this automatically for you when you call this pass, right? So when you do this get compiled pass with the Qiskit extension, it will automatically rewrite this into the circuit you need. Okay. Now, what is if you want to do a random circuit? So this is just an example for a random circuit, which you can generate. But the point here is that you can also so you can also add some other pass in PyTicket, which is called the full peephole optimized pass. So this pass now looks at specific structures of your circuit and makes it even more efficient. So what I want to show you here is, here you have your PyTicket circuit. This is a random circuit I generated. I rebased that into the IBM gate set, applied that rebase pass, and then I'm writing out the number of 2-qubit gates and total gates. So the number of total gates is 26. The number of 2-qubit gates is 3. So now if I apply the full peephole optimized pass, which is a very powerful pass in PyTicket, we just apply that now to our circuit. You see here, full peephole optimized dot apply to a random circuit. If I do that, suddenly I can decrease the total number of gates from 26 to 9 with just one pass. So this is now, if you want to reduce the number of 2-qubit gates, this is very powerful because you went from 26 to 9. You can also have your own pass sequence if you wish. So you can apply your multiple passes. So imagine you want to do your own full hold B optimize and auto rebase pass. You add the sequence pass, and then you adding the auto rebase pass. Here again, you find it. And then you define a pass sequence. So the full B optimize and the IBM optimize, you put that together in one sequence pass, and then you apply that sequence pass to your circuit. So I will share this coding notebook with you. I'm just gonna upload it onto the GitHub. Sorry, it's always a GitHub, onto the Discord channel for you. So the part of the notebook that is available for you right now is how to connect to the backend and how to do the compilation part here. What I want to show you here with the examples I added is that you can actually define your own compilation paths. This is how to generate random circuits, but this is how to do your own rebase paths and how to put it together. So when you go back to this PyTicket Quantinuum, for example, web page, and you see optimization level 0, optimization level 1, optimization level 2, under the hood, what happens is that TKET is defining these passes for you, these sequence passes, based on what's listed here. So you can add your own passes, you can reproduce these passes, you can keep some of these passes out if you wish, but you can totally mix and match the passes you wish on TKET that work best for you. So this is the part of this is how you connect, that's how you compile. So in principle, what you can do is you can take the circuit, right, and figure out how big your circuit would be for IBM backend, and then compare it to the Quantinuum backend. Okay, so now let's look at we have 15 minutes, so let's go first into the now I want you to open up the next one, which would be mid-circuit measurement. See, wait for that to load. Okay, so mid-circuit measurement. So mid-circuit measurement is a tool, as I said before, that allows you to do error correction, teleportation, then also, for example, making the QAA algorithm smaller, if you wish, at least like use less resources. What this sample notebook here for Quantinuum shows you is how to apply that to a 3-qubit repetition code. So this is where you start in the notebook. So for repetition code, as you know, you have to use mid-circuit measurement, and PyTicket has this nicely set up for you. And it goes as follows. So you implement your op types and then your circuit rendering. That's how you code it. We'll do a setup with a repetition code with mid-circuit measurements, 3-qubit. So we have data qubits, and we have syndromes, and we have ancillas. So I won't be able to go through the details of the repetition code, obviously, in the time frame, but I just want to let you know that here's a notebook you can run in order to explore this. So you have a circuit, we call it repetition code, circuit not defined. Okay, so if you get that, then you have to run this here. So I have to run from PyTicket circuit. So because circuit, this is our class we have to call. So you run this, then you have to add your qubit registers and data qubits. Next, you want to have your ancillas. And then you want to have your syndrome, right? So you want to measure out the syndrome. And then you also need a register. So this is now your circuit. you defined everything, and now you're adding this here. So you take a circuit, you are adding a reset to the ancilla qubit. You are having a C0 gate between the data qubit and the ancilla 0. The circuit, now you add to qubit gate to the data qubit 1 and ancilla qubit 0. And then you measure out the ancilla 0, right, which you set up, with the syndrome 0. Okay, let's run this. So this is what you do here. So this is how you set it up. So reset. This is your data qubit with ancillar. This is your ancillar with the data 1 qubit. And then you have, you see, you have, this is your measurement output. Let's see if we can render nested. Okay, so I wonder if I can. Oh, collapse. So you don't want to collapse the classical register. So it's don't collapse it. So what I want you to show here is you actually have multiple, outputs here, but this is what we encoded right now. So this part of the circuit. Okay, let's go back up here. Now we do syndrome extractions. So again, this is for the petition code. We run this. So if the syndrome equals 1, we get a 0, 1, you have to check it, and then may have to apply an X qubit on qubit 0. We also can do the second syndrome, and then the third one. Okay, and then we can measure it all out, and we can run that. So in any case, what I want to show you here, and I think you're gonna collapse this back, is that in TKET, what you can do is you can reset your qubit with this command, and then you can measure it out with the C basis here. On the C basis, you can reset again, measure it out, you can entangle it, and then here you have your different syndromes. And this here, if I can zoom in a little bit. These are your conditional gates, right? So if this is 0, apply, if this is 1, apply X, or else nothing. So in any case, this is how you set it up. If you want to run it on a device now, in this case, you would have to have access to the Quantinuum API. But I do want to show you how that would look like if you have access. So you apply again your Quantinuum backend. This is your machine device name. You log into your device. In this case, you have to set up an account. So if you get access to the Quantinuum device, this is how you would log in. So it will tell you, so H12E, this is the emulator I'm accessing right now. You can print out the status of the machine. So it tells you right now it's online. Then the next thing you would do is you do a circuit compilation. And then again, you would maybe want to look at this. So we run an optimization level 1. You can also do optimization level 2 if you want. Right? So you can see that now this is the phased X, CC phase. So this is the basis gate set of our device, and it rewrites the whole circuit accordingly. Then if you want to process this on a trapped ion device, this is something users sometimes forget to do, is the trapped ion device doesn't need as many shots as a superconducting device. So typically 100 to 1,000 shots are more than enough. A lot of our circuits run with way less than 1,000 shots. So that's important to know, so you don't have to use that many shots on a Quantinuum device. So right now it says, it's just a handle, and you can print out a status of the job with the status handle, and it will tell you the circuit is right now queued. We do the repetition code. It tells you the submission date. It will tell you the queue position, and it will tell you the cost. So this is the HQCs that will tell you about when you run the device. So in any case, right now, because we are in a queue, as you can see, so right now actually it's out of the queue already. But in any case, we are in a queue, so we can't do the results right now. But in any case, if you submit it to the H-series device, this is how it would look like if you, once you get an account set up, go through Microsoft Azure. You would use a different extension, but in principle, same thing. So where you set up, you log in to the backend, and then you would go from there. Okay, so in any case, there's a lot of features you can look at. For example, the arbitrary CC notebook you can open up, and this really shows you how arbitrary CC angle, because you can do an arbitrary angle, how it can reduce your number of 2 qubit gates for quantum Fourier transform. So this is how you would, this is a quantum Fourier transform code example. If you want to go through this to actually realize how many less 2 qubit gates you're using because of this arbitrary CC phase. So you can go through this notebook, but really what I want to do at the end now, with the last time I have, is to just show you, this is a coding notebook I will share with you, show you how PyTicket can help you when you use Qiskit, because I think a lot of you are Qiskit users. And I want to show you how the difference is when you actually apply that to your Qiskit backend. For this to work, you have to have a Qiskit IBM Quantum account. So we'll go through that because we can't set up an IBM Quantum account quickly. I will show you the slides, but I will share this with you. Okay. So requirements again is pip install PyTicket, MATLAB blip is something you normally use. Pip install PyTicket Qiskit now. This is actually something we don't need because we're just using Qiskit. So PyTicket and PyTicket Qiskit is something you would install. Then this is very familiar to you, I hope. This is how you set up the IBM provider, right? So now we're actually coding in Qiskit. So this is your Qiskit way of implementing your code. You're setting up your IBM provider, your Qiskit runtime. You setting up your instance, your token. In this case, I had to do override true for me, but you don't need that override true. You can leave this out. And then you can also save your account information for later. So this is something you need to set up given you're a Qiskit user. Then, for example, if you want to set up IBM Jakarta backend, you are setting it up this way. So this, again, it's very native for you to code in Qiskit. Then you are, Qiskit has a function to generate a random circuit, which we are doing here right now. So we're doing a 7-qubit circuit, depth of 9. So you have 9 layers. And then we just do some measure at the measure, and we have a seed. I don't know what max operands stands for, but in any case, and you can then draw the circuit. So this is your Qiskit circuit. So now I want you to show you how you can get from the Qiskit circuit to the PyTicket circuit to use the PyTicket transpiler or compiler. So if you would now you set up the backend, right, in your Qiskit, your backend, and now you want to transpile it to the backend. So Qiskit has the transpile call, which is optimization level 3, right? This is the highest optimization level. And you can call it, and then you can count out your operators, your gates. So in this case, we want to focus on this number here. You have 104 2-qubit gates. Okay. Now I want to show you what you need to do in order to, if you code in Qiskit up to here, what do you do now in order to bring in Ticket to get a to possibly reduce the number of 2-qubit gates? So you have to have pip install PyTicket and PyTicket Qiskit. Then you are now import the ticket backend. So PyTicket.extension.Qiskit, import the IBM backend, the same backend we just talked about. And now this is very important here. So now you can actually rewrite a ticket circuit into a Qiskit circuit or a Qiskit circuit into a ticket circuit. So you're doing this from PyTicket extensions. You now do ticket QC Qiskit to ticket transpiled QC. So Qiskit to ticket. And transpiled QC is just what we got an output here. So if you go back up, this is your transpiled circuit you got out of KISSKIT, right? With optimization level 3. So now we take that transpiled circuit, we rewrite that into TKET, KISSKIT to TKET to get a TKET circuit. And now we can, this is now rewritten in TKET. And now what you can do is you can do your TKET backend, which we defined, and now we do the get compiled TKET, the get compiled circuit pass using the TKET circuit, which we rewrote from the KISSKIT circuit. And this is optimization level 2 by default. So I didn't write optimization 2, but this is optimization 2, level 2 by default. So you would write here optimization level equals 2 if you want to write it out. But in any case, if you run that now, see here, now you have 93 2-qubit gates. So you went from your KISSKIT gate, the 2-qubit gate count, using transpile level optimization level 3, which was 104, you went to 90 by adding how many lines of code? So you have to do the optimization pass. You have to convert it from KISSKIT to TKET, and you have to import the pass, and then you have to import the backend. So it's 1, 2, 3, 4, 5 lines of code, and you went from 104 2-qubit gates to 93 2-qubit gates. So this is a 10% reduction, right? It's significant. I tell you, if you run the random circuit multiple times, obviously this gate number is going to change. But just want to show you that by adding a few lines of code into your KISSKIT compilation flow, you can reduce the number of 2-qubit gates potentially, right? So obviously you have to play around with your circuit. And then actually you can go back. So you can also go back. So now if you want to go back to your KISSKIT code, you could do that too. So for example, if you wanted to go back, so I'll show you this now. So this is our PyTicket compiled QC. This is our PyTicket circuit, right? So what you can do now is you can write this back into your KISSKIT code. So let's make this bigger. So now we go from KISSKIT to TKET. So KISSKIT to TKET. Oh, that's okay. Yeah. So this is sorry, I was right there. So so you can go from TKET back to KISSKIT with this command. So this is what I want to outline. So so you can use the TKET compiler and then go back into your KISSKIT gate set if you wish. Okay, so incorporating TKET into your workflow really makes a difference. So you can just try it out, okay, and see if it works. So now I want to show you one more thing here. And again, I will share this notebook with you, but again, you need to have an IBM Q account for you to make it work. This part now you can run in principle. So we are setting up the Quantinuum backend again with the non-API function. We are adding the CC phase gate, and now we're doing get compiled circuit optimization level 2 for the H series. So now what we do is we're taking this circuit, which is compiled to the IBM backend, right? And you have 100 or 90 2-qubit gates. I take the same circuit now and I run it on the H series device. So when you do that, you set this up so you have the API information for this. So you can do this if you're a KISSKIT user. You can set up this part for the Quantinuum with PyTicket and PyTicket Quantinuum. You add these lines of code, and then you can compile the circuit for the Quantinuum backend, okay? And what I want to tell you now here, if you do that, you now have number of 2-qubit gates 32. And this is because the Quantinuum device is fully connected. This is why you don't need as many swap gates than you need on the IBM device. And you can really reduce this number by 32. And this is why when I showed you earlier, full connectivity is a unique feature for the trapped ion quantum computers, because you can move the ions around physically. And because of that, you don't have to do the swap gates, which are very expensive for 2-qubit gates. And you can reduce your number of 2-qubit gates significantly, which really makes a difference. So what I would tell you, when you get to a point when you do research and such, you can use, again, I'm going to share this with you in the Discord channel. I will post it right after I'm done lecturing. But you can add this pip install PyTicket, pip install PyTicket Qiskit. You can add these lines of code, and then you can compile it, and you can see if your code, if your problem would have less 2-qubit gates on the Quantinuum device than on the IBM device. And then you can decide for your research if you would like to get access via the Oak Ridge user program, for example. It would be if you can run on the IBM on the H series device, or you can use the free credits we have through Microsoft Azure. So in any case, I think it gives you the tools to try out the H series device, to experiment what it would mean for your application. If you can reduce the number of 2-qubit gates, and hence if you can reduce the error, the noise in your algorithm. With that being said, I think I'm just going to stop here now, and I take more questions, and I'll go from there.
Oh, wonderful. Thanks a lot, KATHRIN, for a great session. The participants have really loved it, and there is a very encouraging discussion going on within the Discord chat. Most of the participants are really, I would say, enthusiastic about trying the notebooks hands-on. So they are eagerly waiting for you to share the notebooks, which I'm sure you would do soon.
Yes.
And yeah, coming on to the questions, there are a couple of questions that I'd like to take. The first one is more of a generalized question. It's regarding the TKET packet itself. You earlier mentioned that it's now open source. So the question is, how can the participants contribute and maybe work towards developing this more?
Yes, so we have a TKET user Slack channel. So when you go onto the GitHub page or our manual, there's something we say like get started with PyTicket. You can access the Slack channel. So once you're in Slack, you're talking to our development teams, like in the direct channel. So you can ask questions right there if you have asks about features and how things work, if you want to compile your circuit, how things get better. So you can ask about this. Or what you can do is, just because it's a GitHub repo, it's a C++ code base, you can add things. You can make pull requests, right, in case there's some feature or something you need changing. So you can do that. So it's open. So open source, it's C++, is the code base of TKET. You can do pull requests on GitHub if you find something that needs changing, or you can communicate with a Slack channel.
Oh, wonderful. Now the question is, now it's a bit more on the technical end, and the question is that optimization generally involves a trade-off between the width and the depth of the circuit. So how does the TKET optimizer handle that?
Yeah, so obviously we want to so it depends, right, man? If you recite mid-circuit measurement is a way for us in TKET. So there's, when you get access to the H series, we have a pass in TKET that does the rewrite for you for the mid-circuit measurement. So it looks for ways of like making your circuit less wide, right? It can't be applied to all of the algorithms. It can be applied to some. You have to try that out. Regarding the how many layers you have, obviously, TKET is also trying by optimization. We have some passes that try to optimize layers on top of 2-qubit gates. So it's really something you have to try out, right? So there's a call, which I didn't do. So you could ask for how many layers do you have, and does TKET help you reduce the number of layers? There's still a lot of like user input needed when you do algorithm development, and that's just something you have to check yourself. TKET is trying to implement tools that are out there, research tools that are out there, compiler passes as it goes and as we develop things, but it's really something you need to try. There's specific passes that do that. I can't like name them on top of my head. We have so many passes, but It uses Lucas for features, and ZX calculus is very powerful to rewrite the def. And I think ZX calculus, as you know, it's a lot of development right now in that field. And as ZX calculus becomes better at giving, us at least the mathematical structure we have to look for, or what we have to look for in circuits, and how to rewrite that, that will be implemented as we go.
Yeah, absolutely makes sense. A follow-up question on that. Does the optimization involve seeing into what hardware it is run on as well, like the topology and the way in which the qubits are arranged on the hardware?
Yes, so TKET takes advantage of all that. So you can go into the PyTicket documentation. There's actually something which is noise-aware placement. So it pulls out the architecture. So for each device, TKET knows the architecture, and IBM is posting their calibration for the qubits. So as we get the information in, TKET pulls that information, and then it places the circuit on the architecture where it's best. TKET decides it's best to be placed on.
Okay, great. Another question I would like to ask is by Ron from Chicago. He asked that, is there a particular framework in PyTicket which allows you to build your own front-end transfer?
Can you repeat that, please?
Ron from Chicago asked that, is there a framework in PyTicket which allows you to build your own front-end trisphaler for different quantum languages?
Yes, so different quantum languages. So so we work with people from different hardware companies, for example, that want to use TKET as their compiler. So this is what QIR comes from now. If your backend can understand QIR, you can use TKET compilation paths to do it. People have written their own backend extensions, so we have notebooks for that, so you can go there. But then on the front end, as I just showed you, you can define your own basis gate set with the rebase bus, whatever you want, right? You can make up your own basis gate set and see what your circuit would look like. You can also make your own connectivity graph. So you can come up with your own, make a three-dimensional quantum computer, see what happens. So TKET can do the connectivity for you. You can actually put that in. So it's a very versatile tool with the functionality there. And if there's something, we can also add errors to gates. So so TKET is actually very has a lot of tools you can use.
Great. Yeah. So thanks a lot once again, KATHRIN. A lot of comments are popping in on the Discord now that it was a wonderful session. It was an excellent session demonstrating this powerful tool of optimization. They loved your session. So yeah, thanks a lot once again. It was a great
you're welcome. You're welcome. And I will post the notebooks now.
Absolutely. And since you're already on Discord as well, I would advise everyone to just keep going on with the questions, and you could take your questions over there as well.
Oh, sure. Yes. Yeah. So I will take the questions as they come in. Super exciting. And tomorrow I'm excited to give you the virtual reality lab tour of our backend. And I will have, hopefully, we'll field the questions. I'm not a hardware expert, but then for that you have the hardware panel later this week, right, Marlou? Yeah. Too,
absolutely.
So,
we will be seeing a lot more of you later this week as well.
But thank you for having me. It's so exciting and very excited. Finally, I was able to speak to the group. So thanks.
Thank you. That was amazing. And looking forward to seeing you tomorrow again for the virtual reality lab tour. Then indeed, right after the hardware panel with Caroline Figot from Quantinuum, who can answer the remaining questions.